All right. So chapter 24 is on electric potential. But before we go to electric potential, we need to define electric potential energy. This is the way the electric potential energy is defined. We say the difference in electric potential energy of a charge between points A and B, like this point and that point, in a static electric field is defined as the work done by external agent to move the charge in equilibrium slowly with negligible acceleration. That's what equilibrium means you move the whatever you're moving very slowly from point A to point B along a path C. At this electric force is conservative, means that the work doesn't depend on the path from A to B. So path is not really that important. No matter which way you go from A to B, it's the same. So this is the way it's defined. The work done, remember from mechanics, the work is external force dot ds integrated over a path from A to B. And it is path independent because the force is conservative. And this is called change in electric potential energy. All right, so we define the change because electric potential energy doesn't matter how much it is at a point, only the difference matters. So this is very similar to the way we define gravitational potential energy in mechanics. Again, that is also integral of F external dot ds from A to B over a path. All right, any questions about that? Okay, so this is the way it is defined. What it means is that you divide the path from A to B into many small pieces of ds, which is a vector along the path, has a small magnitude. At that point, you see what is the external agent that keeps the charge moving. So that's F external at that point. And then you calculate F external at that point dot ds. You get a scalar. And you get a number. And then you add all of that, similar things from A to B as you go along the path. All right, so that's the way it is defined. But because we say we're going in equilibrium, means that the negligible acceleration means that the charge is not accelerating. The net force acting on it is zero. The external force plus the electric force is equal to zero. So if external should be equal to negative of force of the electric field on the charge, which is Q times E. Right? Force of electric field is the charge that we are taking from A to B times the electric field at any point. So the change in electric potential energy can be written in terms of this electric field. And delta U, it becomes negative Q times E dot ds from A to B, right? So this is basically that because the F external is negative QE. So we can write in terms of the electric field. All right, so let's put that up here. Usually we define potential energy to be zero at the reference point, which some often take it at infinity unless we have infinite charge distribution. For example, if you have an infinite line of charge, then you cannot take the reference point at infinity because then at any point the electric potential energy will be infinite. And or if you have a plane of charge or something, anyway, any infinite distribution of charge, we may take a reference point at any other point. So the potential energy of charge at any other point with position vector r is with respect to that reference point will be U at any point r is equal to negative Q integral from infinity to r, or from reference point to r of E dot ds. So sometimes this reference point is infinity, but sometimes it is not. So now what is the electric potential? This was electric potential energy. And the chapter is about electric potential. So the way we define the electric potential is this. We define the electric potential, we call it V of R as opposed to U of R at any point in space around the charge distribution with position vector R, means the point is at position vector R. We define the electric potential as the electric potential energy of the test charge, Q naught, when placed at that position, divided by the charge Q naught. All right, so it means if you have charge Q naught has some electric potential energy, you divide the energy by Q naught, you get that is electric potential. So potential is potential energy divided by Q naught. Or anywhere you want to find electric potential energy of some charge, you multiply the charge by the potential, you get the potential energy. Or V, if you divide this by Q, you see that V at any point is equal to negative integral from the reference point, which is sometimes infinity, usually infinity if you have a finite charge distribution, to a position vector R E dot ds. And it doesn't matter which way you go from infinity or from reference point to R. Okay. So this is definition of electric potential. But we have the difference in electric potential between points A and B in a static electric field of a charge distribution as this. You see, from A to B, the difference in potential, the potential difference is the more important thing, not the potential at any point. Because what actually makes a difference is the difference of the potential, delta V, from one point to the other, not the actual value of the potential, like as you saw in mechanics. All right, so delta V is equal to VB minus VA. When we say delta V means final minus initial, which is the negative of the integral from A to B of E dot ds. Again, you do the same thing from A to B. There is a path. You choose a path to take from A to B and this integral of E dot ds. Of course, we're not going to do that, but this is the definition. When we define the potential to be zero at a reference point, which is sometimes at infinity, we take from reference point to R, that becomes the potential at any point R, because now we have a reference point. And once we have a charge distribution that sets up a potential field in space, the electric potential energy of a charge Q that is not part of the charge distribution is given by Q times V. U is equal to Q times V. Remember, V was defined as U over Q. So we do cross, it is the same as cross multiplying the same formula. So this is the way the electric potential is defined between 2 points, change of electric potential between 2 points. If you have a reference point, that is the potential at any point compared to the reference point. And now for any point, you have a potential, electric potential. And then if you have a charge at that position, it has a potential energy. The charge has a potential energy that is the charge times the potential. All right? Does it make sense? Any questions? All right. Now, what is the unit of electric potential? From this formula, you see, or this formula, you see that the unit of potential is unit of electric field times unit of distance, which is meter, which is Newton per Coulomb times meter. Or from here, this is potential energy. The unit of energy everywhere in physics is joules. And therefore, unit of potential becomes joule per Coulomb, right? Unit of electric potential V is joules per Coulomb, or Newton meters per Coulomb. All right, Newton meter per Coulomb. Joule is Newton per Newton meter. Or you can say Newton meter per Coulomb, or you can say Newton per coulomb, which is E, times meter. You see, this is Newton per coulomb times meters. All right. We call this unit a volt. We don't call it joule per coulomb or Newton meter per coulomb. We call it joule. We call it volt, and it's denoted by V. It is, for some reason, both the quantity and its unit are denoted by V. All right. 1 volt is 1 Newton meter per coulomb or 1 joule per coulomb. Therefore, the unit of the electric field is given as Newton per coulomb, as we had before, or you can now say it is volt per meter, right? Because this unit of this energy, this electric field, this has unit of volt, this is meter, so electric field will be volt per meter, okay? Or joules per coulomb is per coulomb is what am I going to say? Yeah, from this formula you can see. From the others you can also say the same thing. So 1 Newton per coulomb is the same as 1 volt per meter. Both of those can be stated as the unit of electric field, and they are the same. They are the same thing. They are both in SI units. All right, this is unit of electric potential. Any questions so far? So this electric potential is very important in physics, and we're going to work on that. So suppose you have 2 points that are distant from each other by delta S, like 1 point here, 1 point there. They're close to each other, but they're not the same point, so there's some delta S. And so from here, if the electric field is fairly constant, we can say, okay, this electric field is constant, integral of ds becomes delta S. So delta V becomes negative E dot delta S at any point. The question is, how can we have 2 points fairly close to each other that have exactly the same electric potential? What does it mean, exactly the 2 points have the same electric potential? It means the electric potential difference between the 2 points is 0. How can we have delta V 0 when delta S is not 0? What do you think? We go from 1 point to the other neighboring point, but potential doesn't change.
Would they have opposite charge?
What? The points don't have charges.
Oh, okay.
Yeah, there are 2 points in space. There's electric field present. The electric field is created by all the charges that are around. I mean, there's no charge at that position. So we want to make a step delta S so that delta V is 0.
Does it have to do with the electric field, or?
Yes, there's electric field present. When there's electric field, one way we have 0 potential is when electric field is 0, right? If the electric field is 0, you dot product any 0 vector by any vector becomes 0. So one of the answers I'm looking for here is that when electric field is 0. If electric field is 0, potential doesn't change, no matter which direction you go, right? But if the electric field is not 0, is it possible to have this quantity 0? E is not 0, delta S is not 0. How can this be 0? You guys don't remember your vector knowledge, dot product. Is it possible to have 2 non-zero vectors and and their dot product is 0. Opposite direction, no, that's not right. Yeah, they should be perpendicular. Yeah, if E and delta S are perpendicular to each other, then E dot ds is 0, right? So if we go in the perpendicular direction to the electric field, we don't get any change in potential. The same as in gravity. If there is a gravity of the Earth, which is directly downward, if you go from one point to the other horizontally, there's no change of electric potential, there is no change of gravitational potential energy or gravitational potential. So there are two answers to this question. There are two ways that the electric potential can be 0. One is delta V is 0 when E is perpendicular to delta S. The other one is delta V is 0 when E is 0. And each one of these cases give you very important messages. So what do we get from this? So when E is perpendicular to delta S, so what happens if you go perpendicular to delta S? In an E field that is not 0, if we always move perpendicular direction to the field lines, we move on a surface with the same electric potential, like horizontal surfaces in gravitational field. So surfaces that are perpendicular to the electric field lines at all points define equipotential surfaces. All right. So if you always go perpendicular to the lines, you go on a surface that is called equipotential surface. For example, here is a simple case where the field lines are these purple lines. They are all parallel to each other. It's a uniform field. And at any point, if you go perpendicular, you move on a plane that's perpendicular to the field lines, you have a plane of equal potentials. So these are called equipotential surfaces, which in this case is flat surface, each one, and because the field is uniform. The same as the gravity on the surface of the Earth, close to the surface, you see that the gravitational field is downward. If you go horizontal in any direction, you're moving on a horizontal plane where everywhere the gravitational potential is 0. Or if you have a mass there, and on that plane, the gravitational potential energy is the same. All right? Change of gravitational potential is 0. If you have a point charge, we know that the electric field of a point charge, if it is positive, it's radially outward, right? And every point is radially outward. So if you move perpendicular to the field at any point, you're moving on a sphere centered at the charge, right? So if you move in the perpendicular direction to the radial direction, if you're on a plane, you're moving on a circle like that. If you are in 3D, you're moving on a sphere, right? So these spheres are equipotential surfaces, but each one has a different potential. We're going to talk about that in a moment. Or if you have two charges, plus and minus, you see that the field lines look like this, okay? And then these are equipotential surfaces, and they are not spheres anymore because this other charge, the presence of other charge creates an electric field that is patterned like that, and it modifies the surfaces, the equipotential surfaces. In this case, you see the middle one is a plane, is a flat plane. If you are in the perpendicular bisector of these two positions, you are on a plane, and the distance to each one of these charges is the same, and they are opposite charges. They create net zero potential, and the potential on that is 0. on the plane of perpendicular bisector of the line segment connecting these two. Okay. And then if you have a sphere of charge and a flat surface, the field lines are like this. As you see, the equipotential surfaces are like that. All right. Any questions? So the fact that when you move in perpendicular direction to the electric field, the potential doesn't change gives us these equipotential surfaces. Does it make sense? All right. Any questions? All right. So it requires a little bit of imagination, of course. And then what happens if E is 0? If E is 0, E dot delta S is 0. See, if E is 0, delta V equals E dot delta S is 0. That also gives us the same potential for the two neighboring points. Since the E field is 0 inside the conductor and is perpendicular to the surface just outside the conductor, all the points in a conductor are always at the same electric potential, of course, in electrostatics. So a conductor defines an equipotential region. This also means that when you connect two conductors of any shape by a conducting wire, the two conductors and the conducting wire are all at the same potential. Why is that? Because inside the conductor, electric field is 0. From any 2 points, from any point to any other point, if you want to go, you can take a path that is all inside the conductor. And you calculate this integral E dot ds. E is 0 along the path everywhere. So E dot ds is 0 everywhere along the path. So you get delta V equal to 0. Means VB minus VA is 0. Means VB is the same as VA, right? So this is very, very important that a conductor and even conductors that are connected by conductors have the same potential. Like these two. This is a conductor, like say copper. This is another copper. They're connected by a wire or conducting wire. So they have the same electric potential due to the definition. From any point here to any point there, you can take a path through the conducting wire and go to the other, and along the way, the electric field is 0. And therefore, E dot ds is 0. So the total integral is 0. Therefore, VB is VB is equal to VA. All right. We don't say VB is 0 or VA is 0. They are the same potential. All right. Any questions? This becomes very important here when in chapter 25, we talk about capacitors. And these are the plates of capacitor. This is one capacitor. This is another capacitor. This is one plate of this capacitor. This is one plate of the other capacitor. And they are connected with the conducting wire. These are conductors connected with conducting wire. So both of these plates of different capacitors are at the same potential, electric potential, okay? And sometimes we have situations like this. You have a capacitor like that, you have another capacitor like that. You see that this conductor, which is the plate of this capacitor, is connected by conducting wires with this one. So these two are in the same potential. And this one is also connected to the other one via this conducting wire. So this plate is also the same as this one potentially, all right? And then the potential across these two means from here to here is the same as from here to here, right? So we say that these two capacitors have the same potential difference across them, and we call them parallel capacitors. We're going to talk about that next chapter. So one of the important messages that we take from this chapter to the next chapter is this. Pay close attention here, okay? We have the same for some resistors that are connected. All right, any questions? That's why you see this electric potential is very important. We're going to use them in the next chapters. All right. What is the electric potential of a point charge? Now we learned a lot about electric potential in general. We want to see specifically for a point charge, what is electric potential of a point charge? So let's say we have a point charge that is at the origin of an electric origin of a coordinate system, X and Y. It creates an electric field everywhere in the space, especially for this point, is radially outward if Q is positive. And of course, if Q is negative, is radially down inward toward this origin. And we can write this electric field, as you know, as a magnitude and direction. Magnitude is KQ over R squared. And the direction is in the direction of R hat, where R is from this point to this point. And so this is the electric field of charge of point charge. Now we want to find the difference of electric potential between point A, which is at the radial position or position vector RA, to point B, which has position vector RB, right? From here to there. And this is the electric field along the path C. So we need to evaluate that integral. Delta V is equal to VB minus VA is equal to negative integral from A to B E dot dr. All right. So we take dr at any point and we perform the integral. Because you know this electric field is radial, it is much simpler if we do this integral in polar coordinates, that R is R vector is denoted by the magnitude of R and angle. Means that R and theta means how far we are from the center and at what direction we are instead of X and Y. Then when we have this, dr means the change in position vector can be written as dr times R hat, means a little bit we can go away from the center in the direction R hat, and a little bit we can go in this direction. So you can split this dr into two components. One is radial, which is dr times R hat. One is azimuthal, which is perpendicular to dr. R hat is the unit vector in the direction of R, and theta hat is the unit vector perpendicular to R hat at any point in counterclockwise direction. Of course, we're talking in the plane. Okay. So now that we have that, what is E dot dr? This is E. This is dr. We want to make a dot product of these two. So E dot dr with the negative sign becomes negative KQR squared dr, because you see R hat is everywhere perpendicular to theta hat. So R hat dot theta hat is 0. R hat dot R hat is 1. So E dot dr becomes only this dr times the magnitude of E. And of course, there's a negative sign in front, so it becomes negative KQ over R squared dr. All right, so the integral, negative integral from A to B, ER dr, becomes just the integral of this quantity then, instead of that. All right, the negative sign can come out, and KQ is constant, comes out. So we have the integral of R to the negative 2 dr. 1 over R squared becomes R to the power negative 2. And then you know what the integral is. You add 1 to the power and divide by the new power. So this becomes R to the negative 1 divided by negative 1, which eliminates this negative. and becomes KQ over R, but then you have to put the R of point A and R of point B. So it becomes like that, KQ 1 over RB minus 1 over RA, right? This is the way we do integral. And then we can write this as V at point P, at point B minus V at point A, right? Or we call it delta V. So you see that V at point B is KQ over R at B. And V at point A is KQ over R for A. So if we take V equal to 0 at infinity, meaning that, for example, if you take the VB, VA equal to 0, and take RA equal to infinity, this goes to 0, and of course, V of B becomes KQ over RB. And you see that for any point, V at any point R is KQ over R. Means that it only depends on the distance, and it has a magnitude of KQ over R. All right? So this is the electric potential of a point charge. Any question? All right, so let's work on this now. The potential is inversely proportional to the distance from the charge, as you see from the formula. And the potential is positive for positive charge Q and negative for negative charge Q. Means if the charge is positive, it creates a positive potential. If the charge is negative, it creates a negative potential. And potential is larger, closer to the charge, and smaller, far away from the charge. If you plot the potential of a point charge as a function of the X and Y, if it is at this, the charge is at the origin, then the potential becomes like this. As you go close to the origin, the potential increases. And in fact, for a point charge becomes infinite. But anyway, we don't have that. Yeah, there's a singularity. All right, any questions? So the electric potential of an isolated spherical conductor. So what if we have a spherical conductor that is isolated, means that there's no other charges around? What is the electric potential of that? You remember that an isolated spherical conductor, it creates a electric field outside of itself, like electric field of a point charge, right? On the outside, the electric field of a uniformly charged sphere is the same as a point charge. The potential is also the same as that of a point charge outside the sphere. So we have this for the sphere as well, because the electric field is the same, therefore the integral will be the same. If the reference point is at infinity, we get the same thing. And since E is equal to 0 inside the conductor, this is a spherical conductor. So remember, inside the conductor, electric field is 0. And it is the case for also uniformly charged spherical shell. So inside the sphere, there's no electric field. What did we say about potential if the electric field is 0? The potential doesn't change, right? So the potential inside is the same as the potential on the surface for a conducting sphere or on a spherical shell, both the same. So on the inside, V of R is KQ over capital R. R is the radius of the sphere. So it means that everywhere inside, the potential is the same as on the surface. So this is this shows the electric field as a function of the distance from the center. Remember, inside is 0, outside is kq over r squared, right? And on the surface become kq over capital R squared. And therefore, the potential becomes like this. Outside is kq over r. On the surface is kq over capital R. Inside is the same as the surface. So it is kq over capital R. So you see there's a discontinuity for the electric field, but potential is continuous. Okay. Any questions? That's pretty much it for this. And then we have this very important example. The reason I present this example is you will see becomes gives you insight to a lot of phenomena that you see in electricity. We have a conducting sphere 1 of radius r1, 8 centimeter with initial charge of q1, which is 70 microcoulomb, let's say, and conducting sphere 2 with radius r2, which is 20 centimeter larger, initially uncharged, so q2 is 0. They are far from each other and electrically insulated. So we connect them by a very thin copper wire. Assuming the wire is thin enough to carry negligible amount of charge, we want to find the final charge on each sphere, q1 prime and q2 prime. And we want to find the surface charge densities of the spheres, sigma 1 prime and sigma 2 prime. What do you think? What can we do to do that? So they are far away from each other, and we're connecting them with a very thin wire. If you want to find how much charge is on each one now, what do? We need equations, right? What is the basic equation we can do? We can use. We can say that, let me see, kq over r is not a, this is not an equation, Jordan. It is an expression. So that gives that's a one step. That gives you the potential for electric potential for each sphere. What equation can be used? You know, in physics, everywhere, when you want to calculate a quantity, you need to write down an equation. The equation comes from some information given or some basic physical law. Like we write Newton's law, F equals ma, or we write conservation of energy, or we write something else. What do we have here? That is an equation. The potential for each one is kq over r, its own q and its own r. But are the potentials the same? We said that if you have two conductors and you connect them with a wire, conducting wire, they have the same potential. All right. So we can write potential of this one equals potential of that one. Right. So, but also we have conservation of charge. We have the new charges q1 prime plus q2 prime is the same as the total charge before, which was q1. So we have q1 prime plus q2 prime equal to q1. On the other hand, the spheres have the same potential. So we have v1 prime equal to v2 prime, which is kq1 prime over r1 equals to kq2 prime over r2, right? So this means potentials are the same, and we have conservation of charge. Of course, some of this charge goes to the other one, right? And therefore, the total charge doesn't change because we have conservation of charge. That's a physical law. Another physical law that we have here, specifically for two conductors connected, have the same potential. And we know that the potential for each sphere is KQ over R. That makes sense? Now, this gives us two equations to solve for two unknowns. You can cancel K, you get this equation and that equation. So these are the two equations to solve for Q1 prime and Q2 prime. So how do we do that? We can find Q2 prime from this equation, put it in there. So from second equation, we have Q2 prime equal to R2 over R1 times Q1 prime. And R2 is 20 centimeter, R1 is 8 centimeters. So 20 divided by 8 times Q1 prime. So that's 2.5 Q1 prime. And then we put for Q2, which is that, we put it here. So we have Q1 prime plus 2.5 Q1 prime equal to Q1. So 3.5 Q1 prime equal to the Q1, which was 70 microcoulomb. And then Q1 prime becomes 20 microcoulomb. So this had 70 microcoulomb. Now it has 20 microcoulomb. Where is the rest? On the other one. So Q2 prime is 2.5 times that, which is 50 microcoulomb. So these are the solutions. All right. So this is part A. Q1 prime and Q2 prime we found 20 and 50. All right. So what is the surface charge density of each sphere? So let's do that one. So we use this equation. See what it gives us. Q1 prime over R1 equals Q2 prime over R2. But we want to find sigma 1 and sigma 2. Sigma 1 prime means the new sigma over the sphere 1 is what? The surface charge density. What is that? Can somebody tell? What is the surface charge density of this sphere? The surface charge density is the total charge it has over its surface divided by the surface area, isn't it? So it becomes Q1 prime divided by 4 pi R1 squared. 4 pi R1 squared is the area of the sphere 1. And the same for the second one, Q2 prime divided by 4 pi R2 prime. R2 squared, sorry. All right, so these are the new charge densities. Of course, we can plug in the numbers. Now we have all of these. We know how much Q1 prime is and R1 is and so forth. We can plug in and get the numbers. That's not very important. Something important I want to see the ratio of their charges and our surface charge densities. So let's calculate sigma 2 prime over sigma 1 prime. If you divide sigma 2, this divide by that, 4 pi's cancel. So you get Q2 over R2 squared divided by Q1 over R1 squared. But we also have this. You can do this. So Q2 is times R1 squared divided by Q1 times R2 squared. But we have this Q2 over Q1 is R2 over R1. We can put that instead of this. So we have this ratio of the sigmas equal to R2 over R1 times R1 squared over R2. So you see this R2 cancels, R1 cancels, so you get R1 over R2. So you see that sigma 2 times R2 equals sigma 1 times R1. All right. What does that tell us? This is very important. The importance of this example is this part. It says that if you have R2 greater than R1, means that sigma 2 is smaller than sigma 1, right? So The larger sphere acquires a larger portion of the charge, but it has a smaller surface charge density. The smaller sphere has a larger surface charge density. All right, this is the importance of this example. The smaller one has larger surface charge density, even though the total charge of this is bigger than this. But the surface charge density on this is bigger than that. All right, why is that important? All right, the question. At the time of possible thunderstorm, why do the authorities order the people at the beach to get out of water and get shelter? Does anybody know that?
Because lightning could strike the body of water and the water can zap you basically.
Yeah, but not exactly. I will explain. If the lightning strikes the water, if you are fairly far away, if it is more than like 10-20 meters from you, you're okay. But the problem is it may hit you. The lightning will hit you. Why is that? I'm going to explain that, okay? So let's go over from basic things that we learned here. I'm going to go over it to see how we get to that. So we said that the smaller sphere has a surface charge density, larger surface charge density, and it has larger curvature. We say the curvature is inverse of the radius. So wherever curvature is larger, the surface charge density is larger. For example, if you have this kind of shape, you see that the surface charge density on these corners is larger. That is what happens if you have a conducting object. It's like wherever there's more curvature like this, compared to this one, there's more surface charge density. So the charges go to the pointy places. If you have something that's very pointy, then the surface charge density over here is much, much larger than the other places. Okay, why is that important? Let me continue. Remember that we said that the electric field just outside the conductor is proportional to the surface charge density, right? With E just outside the conductor was sigma over epsilon naught. Remember that? We calculated in Gauss law. So the electric field is much stronger near the sharp edges of a conductor. It means close to here, the electric field is much larger than here, all right? This large electric field polarizes the air molecules near the sharp areas and makes the air more likely to ionize or break when there is a possibility of discharge, all right? If the E field is stronger than 3 million volt per meter, the air ionizes and becomes conducting. Means that the electrons get separated from their molecule and jump to the other molecules, right? And therefore the gas becomes conductor, conducts electricity, and that is the electric discharge that you see lightning. Why you see lightning, why it creates light is another story. While the electrons are jumping from one to another, hit other electrons in the molecule, and the electrons go to a higher level of quantum levels of energy that they have in the molecule. And then after a while, very fast, of course, in nanoseconds or microseconds, they come back to their original point and they give light. They give a photon of light. That's why when that happens, you see a light, and of course, you hear a sound, and sound because it creates a very large wave in the air. So this is what lightning is, okay? In a thunderstorm, the electric charges accumulate in the clouds near the Earth's surface This induces opposite charges on the surface of the Earth. The sharp points of the Earth surface features get larger density, charge density, which makes them more likely to get struck by lightning. These sharp edges could be a tip of a tree or a building structure or head of a person if there's nothing else above you. You see these pictures of lightning? You see it hit this point. Why is that? Because the electric field is larger. You see when the clouds are charged, they induced opposite charges into these structures, and then there's charge everywhere, but there's more surface charge density on these pointy points. You see here, everywhere you see this one hit one of the posts. This one hit, you see this one, all of them hit only at the places where there is a sharp point. So you understand that because at that point there's more electric field, there's more charge density, and there's more electric field, and then the air is more likely to break at those points. That's why it never hits here, for example. It never hits in the middle here. It just either this side or this side. All right. And you see on large buildings, they put this pointy rod at the top. They call it lightning rod. They are connected to thick conducting wires that direct the large current to the earth and protect the building. All right. And it always hits that. It doesn't hit anything else because that is taller, closer to the clouds, and also it's pointier. And that's why they always hit it. All right. And now getting back to our original question. This is a beach. You're standing here. There's no trees around. It's only flat water. The clouds get charged. And then they induced opposite charges. How is the charge distributed? Where is flat, there's little charge density. Where is pointy, there's more charge density. And there's more electric field here. This is more likely, here is more likely to break. So it is not that, you know, lightning hits you by chance. It's going to hit you by a very, very high chance. And then you get toasted. Okay, if you are in the beach, you are the pointiest stuff. You are the pointy place. It hits you. That's why they say, good, get out of the water. All right. But if there are some trees nearby, the trees are pointier and closer, then you're safe. Unless you are very close to the tree. Of course, there's these currents that go down is in the order of millions and thousands of amps. So there's another thing we're going to talk about later on in the next chapters, that if you lay down, the chance of being hit is lower. If there's something above you, that the chance of getting hit is lower, especially in the water. It's because it's very flat. If the water is calm, it's very flat, and you are the only pointy object over there. It is very likely that it hits you. If it happens that the cloud above you is hitting something, it hits you. And this is why, and some people think that there's something wrong with the water. And even if they are home and there's thunderstorm, they get out of the water in their pools. That is not necessary. They think that there's something wrong with water. There's nothing wrong with the water. It's just in the beach, because there's a very vast flat area and you are the pointy object, it hits you. But at home, if there are trees around, the buildings around, it hits the buildings. Okay? Unless it hits the tree right beside you or the building right beside you in the 10-meter radius, then you may get a little bit of shock. Not some, most of the time, that's not fatal either. We are going to talk about that because the current has to go somewhere. The current comes and it distributes like a hemisphere in the earth. And if you're too close to it, there's a potential difference across your body, and that gives you a shock, not the lightning itself. All right. So this is what happens. Any questions? All right. So this was, you see, from that example, we get understanding of what happens here. All right. That's that subject. Then we go to, what if we have electric potential? We want to see what is the electric field. So far, we say that the electric potential comes from the electric field. You do the integral of electric field, you get the electric potential difference between 2 points. But what if we want to do the opposite? If we have electric potential, we want to find electric field. Again, we look at the original formula. Delta V is equal to negative integral E dot ds from A to B. And if you take a small step, for any small step, dV is negative E dot ds. So this is basically, we can say this delta V is integral of dV. Therefore, dV is negative E dot ds. Means if you have an electric field, you make a small step, ds, in some direction, E dot ds becomes dV. This can be viewed as the change dV in the electric potential during the small displacement ds that is equal to negative of the component of the electric field in the direction of ds. Right? Remember, this dot product can be viewed as the component of E along the direction of ds. So we can now take a small displacement ds to be in the x direction. So ds is dx times I hat. Means that we are taking the step in the x direction with the magnitude dx. Okay. And now what do we get? We get E dot ds equal to delta V. So the dV becomes negative E dot dx I hat. So if you do a dot product of E by I hat, what do you get? This E has 3 components, Ex I hat plus Ey j hat plus Ez k hat. The dot product of j hat dot I hat is 0, k hat dot I hat is 0. The only part that's not 0 is I hat dot I hat, and that it has a coefficient Ex. So this becomes negative Ex times dx, right? dV is negative Ex times dx. And therefore, Ex is negative of dV over dx. But V is a function of 3 dimensions, usually x, y, z. If it is that, we have to use partial derivative. So we say Ex is negative of partial of V with respect to x. So the x component of electric field is negative of partial derivative potential with respect to x. And you can do the same thing for y direction. Take the ds in the y direction, dy I hat, j hat, or dz k hat. Then you get this for the x. Ey is negative partial derivative of v with respect to y. Ez is negative partial derivative of v with respect to z. And we have these 3 equations. So if you have the potential, which is a scalar as a function of x, y, z, you can find the electric field exactly at any point by taking derivative of the potential. And you see the potential is integral of the electric field. Electric field is derivative of potential. And if we put these three together, we can write, there's a del operator, which we can say E is negative gradient of V. This is with this del operator. I don't know, maybe I should elaborate on that. This, I don't know if you have heard about this gradient. There's a del operator, which of course has this. This has three components. As the del over del x is the x component, del over del y is the y component, and del over del z is the z component. And this can operate on something. So if del v, which is gradient of v, becomes has three components basically, is del v over del x, del v over del y, and del v over del z. And as you see, these are the negative of components of electric field. So we say electric field is negative of gradient of v. All right. So this is a compact form of all these three equations. Excuse me. Any questions? All right. So how do we calculate the electric potential due to a group of charged particles? So if you have a one charged particle, we know the electric potential is just kq over r, the distance r from that particle. We just calculated that. But if you have many charged particles, if you have many charged particles, each one creates an electric field, and electric field at any point in space is equal to E1 plus E2 plus E3 and so forth, right? So however many point particles you have. So because electric field is following the superposition law, and then the delta V is equal to negative integral of E dot ds, right? And from A to B, whatever. And then if E is sum of these, then you know the dot product is distributive. So we can write negative integral of E1 dot ds plus E2 dot ds and so forth, right? And then you can break the integral is linear, so you can just do integral of negative integral of E1 dot ds minus integral of E2 dot ds and so forth. It means that delta V is delta V1 plus delta V2 plus delta V3 and so forth from individual charges, or the total potential at any point is equal to, or let me write specifically, at any position vector r is V1 at position vector r, because at infinity all of them are 0, plus V2 at position vector r plus V3 and so forth. So you see that the potentials are additive like scalars. And remember, I'm sorry, I'm losing my voice. And so remember that we said that if a charge is positive, it creates a positive potential KQ over R. If it is negative, it creates negative potential because Q can be positive, negative. So this for each particle, potential at any point is just KQ over R. This is literally with the sign of Q. Positive creates a positive potential, negative creates a negative potential. So if you have a group of charged particles, you can just add the individual electric potential for each one. So here is a group of charged particle Q1, Q2, Q3, in general QI, and we want to find the electric potential at point P due to all of these. So we simply add the electric potential. We say V is equal to sum of VI, which is KQI over RI. So RI is the direct distance from each charge to that point where we want to calculate the potential. All right. So you see R1 is this direct distance, R2 is that direct distance, and so forth. So note that the positive charges create positive potential, negative charges create negative potentials, and the summation is an algebraic sum, not a vector sum. That makes an advantage for working with electric potential as opposed to the electric field, because calculating algebraic sum is much easier than calculating vector sum. Instead of adding vectors, just add numbers. That's a lot easier, right? So this is the way it works. This is an example. You have Q1, Q2, and Q3. Q1 is 10 nanocoulomb, Q2 is negative 20 nanocoulomb, and Q3 is 30 nanocoulomb at these positions. P1 at positions P1, 0, 0 at the origin, P2 at 5 meters and 0, and P3 at 4 meters on the y-axis, respectively. Find the total potential due to these charges at the position P of 2 meters and 1 meter. That's this point, P. So we need to calculate the direct distance from each charge to P. For example, this R1 can be calculated by the square root of 2 minus 1. You see the change, difference of the x's and difference of the y's squared. Remember this distance between 2 points, square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so we have this. So R2 is square root of 5 minus 2 squared plus 1 minus 0 squared, which is square root of 10. R3 is 2 minus 0 squared and 4 minus 1 squared, which is square root of 13. So V is V1 plus V2 plus V3, which is KQ1 over R1, KQ2 over R2, KQ3 over R3. K can be factored, so we have that. So V is 9 times 10 to the 9. Q1 over R1 is 10 times 10 to the negative 9 over square root of 5. The other one is negative 20 times square root of times 10 to the 9 over square root of 10. And the next one is 30. The two of them are positive, one of them is negative. So it creates, this one creates a negative electric potential. And then 10 to the 9 and 10 to the negative 9s cancel out, and you can write it this way. And then if you calculate the whole thing, it comes 58.2 volts. So this potential at this point is 58.2 volt due to all three charges. All right. All right, what if you have a charge distribution? Excuse me. What if you have a charge distribution like this, a continuous charge distribution, not a collection of points? For this, we take a small piece of that, small enough so that at point P, it looks like a small charged particle. And at distance R. Then we say the total potential is integral of small dv created by this. This dq creates a dv here. dv is k, the charge of that dq divided by r. So if you put that for dv, k can come out, becomes k integral of dq over r. And r is the direct distance from dq to p. All right. So if you want to apply that to this ring of charge on the axis, we take a small piece of that and see what is the distance here. And of course, there's a distance r here, and this is a right angle. So this r is what? It's square root of r squared plus z squared, right? So the dv for that piece, if it has dq, dv is equal to k dq over r, which is k dq divided by this square root, r squared plus z squared, right? And then v becomes the integral of dv, which is k can come out, integral of dq over r squared, square root of r squared z squared. But then we have to move this dq around and add all these contributions here. But as dq moves around, does this quantity change? The z is constant, r is constant, so the whole thing is constant. So that one also comes up. So k over square root of r squared plus z squared. And then integral of dq. Means adding all these dq pieces together. So what do we get? We get the total charge. So v becomes k q over this distance r squared plus z squared. So you see, because all of the charges are at the same distance to point P, becomes kq over distance of each the charges. So they all add up and we get a very simple formula. So it becomes kq over square root of z squared plus r squared. And then, as I said, they are all the same distance. Note that from this potential, we can derive the electric field. What time is it? It's almost done. So I'm going to stop here. We take it from here next time, right? So sorry, my my voice is not very good. I don't know what happened to me. All right. So I'm going to stop.